In this video, I'm looking at proton NMR peak splitting, and that's caused by something known as spin-spin coupling. And what does that mean? It's the interference between adjacent non-equivalent nuclei. So basically, nuclei in different environments interact with each other or couple with each other and causes the peaks to be split. So the first thing to show you is the proton NMR spectrum for ethanol. So going back to ethanol, would look something like this if peak splitting was shown in the spectrum. So remember, the environment, the shift value tells us the environment. So the green protons are resonating somewhere between 1 and 2, and they are coming out in a pattern that we call a triplet. So that's got 3 peaks to it. The blue protons, somewhere between 3 and 4, they come out as what we call a quartet. So we've got 4 peaks, and the red proton is coming out as what we call a singlet. So it starts to get a little bit complicated now. I'm going to try and do it as simply as possible. So first thing I want to point out is the 3 bonds apart rule. So splitting can only be caused by protons in a different environment that are no more than 3 bonds apart. So if we look at the green signal, or the green protons, the blue protons are in a different environment. Are they no more than 3 bonds apart? 1, 2, 3. So yes, the blue protons can split the green protons and vice versa. Unfortunately, the OH protons are problematic, and they require almost a video to themselves. So I'm just going to give you a very simple explanation at the moment of when I get onto the red proton. So what's causing the splitting? Well, we think about how NMR works. This is why it's helpful to know about the spin states, sort of how much energy it takes to resonate the spin states. What happens is the adjacent protons that are no more than 3 bonds apart in a different environment, hope that's not too complicated to start with, their different magnetic field affects the magnetic fields that these protons experience. And if we consider these 2 protons, we could think about their 2 spin states could both be up. Their 2 spin states could both be down. And also their 2 spin states could be, this one could be up and this one could be down, or this one could be up and this one could be down. And so these 2 protons actually have 3 different, slightly different magnetic fields associated with them, and so therefore they can affect these equivalent protons in 3 different ways. And that's why we see a triplet when 2 protons are adjacent. In the case of how would the CH3 protons, how would they affect this environment here? Well, we know that these protons actually come out as a quartet, and that's because the spin states of these green protons can have 4 different possible spin orientations. So there's the 3 for the CH2s. It's a bit more complicated for the CH3 protons. But essentially, there's 4 different magnetic fields possible when you have 3 adjacent protons. And so they will affect the magnetic moment of these protons in 4 different ways. Now hopefully I haven't confused you so much that you've turned the video off and you're still with me. I'm going to tell you a much easier way to work out what the splitting pattern tells you, and that's this n+1 rule. So if we look at the green signal from the green protons, what's adjacent to the green protons? CH2 group, and so n is 2, the number of adjacent protons that are in a different environment. 2 + 1 is 3. So when you've got a CH2 group adjacent, then the signal for these protons would be split in 3 ways. So you see the triplet. The blue protons adjacent to 3, so n is 3. So we see n+1, 3 + 1, 4 peaks. So we see the quartet. Now, if you think about the hydrogen, the red hydrogen in the OH environment, that's still within the 3 bonds apart, 1, 2, 3 bonds, but OH protons are always seen as singlets. So we'll look at a worked example now. I've drawn an ester on the board there. So this is ethyl ethanoate. What you can have a go at doing is having a go at sketching the high resolution NMR spectrum for this. So what sort of things would you need to be able to include? How many peaks, where they would be, so what their shift value would be, what the splitting pattern would look like for each peak, and what the relative peak areas would be. So we'll start with the easiest one, that's the number of peaks. We've obviously got CH3 group in a different environment to this CH3 group. So these are 2 separate environments. That's the only CH2 group. So we've got 1, 2, 3 environments. So if we look at shift values now, we'll start with the red environment. So that's hydrogen to carbon with a double bonded oxygen on. And you can see hopefully on my data sheet, there's the environment there. Hydrogen to carbon bonded to a C double bond O. Hydrogen to carbon bonded to a C double bond O. So that's somewhere between delta 2 and 3. If we look at the blue environment now, we've got a hydrogen bonded to a carbon, singly bonded to an oxygen. So there's that environment there. Hydrogen to carbon, singly bonded to an oxygen. So that's about 3.3 to 4.2. And the green environment is just hydrogen to carbon to another CH. And so that's the straightforward RCH group. So that's just before 1, so like 0.8 to 2. So we'll start closest to 0 to the TMS peak. So we've got the green environment here. What would that come out as? Well, let's look at what it's adjacent to. It's adjacent to 2, n+1, so 2 + 1 is 3. So we will see a triplet somewhere between 0.8 and 2, so we'll go for here, shall we? So triplet due to these green protons here. If we move to the blue proton environment, so we're between 3.3 and 4.2, and so we would see, well, what's adjacent? CH3, 3 + 1 is 4, so we're going to see something, let's go here, quartet, 1, 2, 3, 4, and then the final one, the reds. Are there any adjacent protons in a different environment within 3 bonds? No, the nearest ones are the blue ones and they're more than 3 bonds away, so they won't cause any splitting of this signal. And so if you think about the n+1 rule, we've got no adjacent protons, so n is 0, plus 1 is 1, and so we see the singlet. We'll finish with the integration values. Sorry, the diagram's changed slightly. I managed to rub the board before I'd said this bit. I've had to draw it all again. The quartet is due to these protons here. So there's 2 in that environment. So that would have a peak area or an integration value of 2. The red proton environment, this one here, well, there's 3 in that environment. So that would be 3. And the green protons, this one here, there's 3 of those as well, and so we'd have integration value of 3. So 2 to 3 to 3.